Hello and welcome to the 2020 IEEE Radio Frequency Integrated Circuits IC Symposium, which is held virtually this year for the first time. This year has been a tough year for all of us, and we definitely did miss the opportunity of seeing all of you in person in our annual gathering. However, to compensate for this, our conference team has worked diligently to put together a stellar virtual event that I hope will be of interest to you all. I am also pleased to announce that as of today morning, our registration numbers for the Microwave Week have surpassed 5,200 registrants, including the exhibition registrations. This puts us on the path to become a record in terms of registration for the Microwave Week lifetime. I would like to start by acknowledging people who could event. First of all, I would like to thank members of our steering committee who spend significant time away from their family, loved ones, and also from their work to support this conference. I am indeed quite blessed and indebted to work with such a great team of individuals. I'll take a few seconds to present the steering committee. Next, I would like to extend my special thanks and gratitude to our executive committee members who all the time have supported me and guided me throughout the year and made sure that we are on track for a stellar conference this year. Thank you. I would also like to introduce and thank our advisory board members. And last but not the least, I would like to acknowledge and thank our exceptional support staff and MPA associates team who have worked tirelessly to bring this event to fruit. Thank you. And finally, I would like to thank our corporate sponsors for their loyal support and unwavering commitment to RFIC throughout the years. Thank you. And now I would like to briefly go over our plenary schedule for today. We're going to start by presenting the highlights of our conference, followed by our student, industry, and Teen Aquatch award ceremony. We will then follow with our two plenary talks. For this year, we are going to feature two visionary talks by distinguished speakers from both industry and academia. The first talk is titled, "Is the Third Wave Coming in CMOS RF?" and will be presented by Dr. Thomas Cho, Executive VP at Samsung Electronics. The second talk will be presented by Professor Ali Hajimiri, the Brent Professor of Electrical and Medical Engineering at California Institute of Technology, and is titled "The Flexible Future of RF." Next, I would like to provide a brief overview of what is included in the Microwave Week virtual event. This year's program is divided into two segments. One will be a live segment, and the other will be a pre-recorded segment. In addition to the plenary session, the RFIC live segment includes the 3-minute thesis, which actually took place earlier today, and the joint IMS and RFIC panel session and a 5G summit, which will take place tomorrow on Wednesday. In addition to the RFIC, the Microwave Week will also host other live events that will encompass both IMS and RFTAG conferences. Moreover, several other pre-recorded events are incorporated into our program. This includes the technical sessions for RFIC, as well as IMS and RFTAG, the technical lectures, and the industry workshops. And to facilitate attendance for people who are not able to join us live or join us this week, I would like to note that access to all of our Microwave Week virtual content is going to be extended through the end of September of this year. And here I would like to highlight a couple of our live events. On Wednesday, we will be hosting a joint panel that is sponsored by both IMS and RFIC, and the panel is going to be streamed live, and the panel is organized by Larry Kushner from Raytheon Technologies. In this panel, we're going to have a distinguished set of panelists who will revisit and debate the idea of digitizing the RF signal at the antenna front end, which will allow for ultimate radio programmability. Immediately following the panel, our highly regarded and attended 5G summit will follow and will take place, again, live streamed through this platform. This year's summit is organized by Walid Ali Ahmed from Samsung Electronics and Tim LaRocca from Northrop Grumman. The summit will feature well-renowned leaders from both industry and labs who will present the latest and greatest 5G and beyond 5G technologies. I highly recommend you tune in to these events. And now I would like to kind of provide you with some reasons why you should actually attend our virtual RFIC symposium this year. I'm not going to go through the top 10 list here, but I'm going to highlight some of my favorites. First, you can binge watch your RFIC presentation nonstop from now until September 30th. Registration is made free this year to all IEEE MTT Society members. You can attend the plenary in shorts, pajama, or anything else. This is, in fact, one of my favorites. You can also attend the exhibition without wandering through a large exhibit hall, dazed and confused as to where the certain exhibitor's booth is located. You can also fast forward through talks if necessary, but please make sure you do not skip the RFIC talks, and because these are always the best. And now I would like to give the floor to Brian Floyd, our TPC chair, to present the technical program highlights.
Thanks, Walid. My name is Brian Floyd, and I'm the Technical Program Committee Chair for this year's RFIC, and I'd like to welcome you to our first virtual RFIC symposium. We have worked tirelessly to produce a top-notch technical program, and our goal is to be the premier and preferred forum for publishing any research breakthrough in RF, millimeter wave, and high-frequency circuits and systems. Now for this year, in addition to switching to the first ever virtual program, highlights for 2020 are numerous. First, this year, we received a highly increased number of submissions compared to prior years, which is a really great indication of the health of research in our field. Additionally, you may be aware that RFIC recently expanded our scope to include systems and applications, since we see this as a really important emerging area of research that exists at the intersection of RFICs and the systems and applications that they support. So this year, we have 2 special sessions devoted to systems and applications. Also, if you are asked to name some of the hottest topics in our field right now, you would likely list millimeter wave and 5G among those. And this is definitely true for this year's RFIC, where over half of our papers are now in this area. This is really exciting to see, particularly as someone who works in the millimeter wave field. Finally, we have organized 2 special sessions on 5G, which together with the 5G Summit, which will live stream tomorrow, should provide an excellent perspective on the latest breakthroughs in 5G technologies. Now, in regards to our submissions, we received 208 papers for review this year, of which we accepted 95. And this is up 27% compared to last year's symposium, which is great. Now, these submissions were coming from all around the world with strong and healthy submissions from each key geographic area. About 1/4 of our submissions came from industry, where the remainder came from academia, where we saw significant growth in the university submissions this year. Now, behind the scenes, we have a really strong team of experts, our technical program committee, who are responsible for reviewing papers for our symposium. And they're all listed here. I would like to thank them for the incredibly hard work that they completed in terms of a double-blind review process for our papers, as well as many other additional activities to help us get ready to launch our virtual platform this year. Thank you, each and every one of you. Now, since this is the first time for all of us to participate in a virtual RFIC symposium, I'd like to point out a few ways for you to access our content. First off, we have the virtual platform, which all of you are now using, where you can access both live streamed and pre-recorded content, as well as attend the IMS virtual exhibition. I invite you to check out all of the content that's on this platform, as there is much to offer here, including 3 complete conference worth of material. Now, one important thing you will wish to do is to view the technical presentations of our authors. All of the presentations have been pre-recorded by our authors and uploaded to the system and are available to you on demand. And this starts from today and lasts through the end of September. This is really an incredible opportunity because now you can binge watch and take in each and every single paper, 95 in total, as often as you like from now to the end of next month. Second, for questions and answers, we have a poll feature enabled in the platform where you can enter questions, and you'll find this directly adjacent to the video that you can watch. And authors can then come in later to respond to those questions. And of course, you can also engage with the authors over email. Now, as far as accessing our papers as well as presentation slides, we actually have 3 methods which you can choose from depending on which you prefer. First, you can batch download all of the presentation and papers as single presentation files. And you can do this by logging in to the RFIC website, not the virtual platform, but the website itself, and then go to the proceedings and presentation slide link, which will then take you to a page to download the files. Second, for a more immediate and easy access to that material, you can go again to the RFIC website, log in, and select the technical program. Then you can navigate to the technical session and then paper of interest and bring up the slides or the paper directly in your web browser. Third, if you really are in love with your mobile device, you can instead use the IMS app and then select the RFIC technical program, and that'll allow you to bring up the slides or the paper directly within that app. Finally, it's hard to believe, but in a little over 10 months will be next year's symposium. RFIC 2021 is scheduled to be held in Atlanta, Georgia in early June of 2021. So please keep an eye out for our call for papers, which should be released onto our website by the end of this month. Leading the technical program for RFIC 2021 is Osama Shana, who I would like now to introduce. He has served as this year's TPC co-chair and will be next year's TPC chair. Thank you for everything you have done, Osama. Let me turn it over to you.
Okay, thank you, Brian, and hi, everyone. My name is Osama Shana. I'm actually the TPC co-chair for this year RFIC Symposium. And I'll be very delighted tonight to present the Best Student Paper Award. The RFIC as a conference pays special attention to student papers and really strives to encourage student paper submission. As committee members, we recognize that our students today are actually the future leaders of our industry. And for this year's Student Paper Award, I would like first to acknowledge Professor Donald Lee from Texas Tech University, who's our 2020 Student Paper Chair, who's the person behind the scene to drive this paper award process throughout end to end. Out of the 208 papers submitted this year, we have received nearly half of those papers being student papers. And we accepted 55 papers of those. And those accepted papers were ranked. And the top 13 student papers were actually selected through a very rigorous double-blind review process and an elaborate voting process. And from those, the top 3 winners has been selected, which I'm going to be announcing shortly. And here is the list of the top 13 student papers for this year in no particular order. And I want to congratulate all of them for the excellent work they've done. Congratulations to all. And now I am going to be announcing the top 3 winners of the Student Papers Award this year. The 3rd place winner goes to University of Michigan, Ann Arbor for their paper titled A 16-Element Fully Integrated 28 GHz Digital Beamformer with In-Package 4x4 Patch Antenna Array and 64 Continuous Time Bandpass Sigma Delta ADCs. Congratulations on this award and for the great work. The 2nd place winner for the Best Student Paper Award this year goes to Columbia University in collaboration with Oregon State University for their paper titled A Scalable 60 GHz 4-Element MIMO Transmitter with a frequency domain multiplexing single wire interface and harmonic rejection based demultiplexing. Congratulations. Finally, I'm now going to announce the winner of the Best Student Paper Award for this year RFIC Symposium. And the winner is University of Pennsylvania for their paper titled A Hybrid Integrated Artificial Mechanoreceptor in 0.18 micron technology. Congratulations for our top 3 winners, and congratulations to all 13 nominees for this award. And I encourage all those students attending this plenary session, wherever you are, to submit your paper to the RFIC Symposium for next year, because who knows, your name may be flashed in the plenary session for next year. Thank you all, and I'll give the microphone back to you, Brian.
Thank you, Osama. Each year, we select industry papers for our Industry Showcase and Best Industry Paper Award. This year, the Industry Showcase is, of course, virtual, where all of the presentations are available on our virtual platform. But these participants also have recorded 3-minute demonstration videos, which are uploaded to IEEE TV, and I invite you to take a look there to get an overview of the full Industry Showcase. I would like to thank Fred Lee from Verily Life Sciences, who is the 2020 Industry Program Chair, for running this contest. This year, we had 47 industry paper submissions, of which 10 were ultimately selected for the Industry Showcase. Now, the Industry Showcase participants are listed here in the next 2 slides, with papers coming from throughout the world. We'll quickly scan through this list here, but you can easily find these papers within the virtual platform by selecting the RFIC Industry Paper Competition tab. So here we have listed the first 4 participants. Next, we have another 4 participants. And then finally, we have 2 more participants. In the top 3 industry paper awards are awarded to, in 3rd place goes to Grit Custom IC for the paper entitled High Resolution CMOS IR UWB Radar for Non-Contact Human Vital Signs Detection. Congratulations and great work. 2nd place goes to CEA Letty for the paper entitled A Reconfigurable SOI CMOS Doherty Power Amplifier Module for Broadband LTE High Power User Equipment Applications. Congratulations, excellent work. And our 1st place award goes to Nokia Bell Labs for the paper entitled A D-Band Radio on Glass Module for Spectrally Efficient and Low-Cost Wireless Backhaul. Great job, congratulations to all. Let me now turn it back over to Walid, who will introduce one final very important award.
Thank you, Brian and Osama, and congratulations to all of our finalists and award winners. And now I would like to announce the winner of another special service award in our symposium, which is the Special Service Award. The Tina Quach Service Award recognizes outstanding service that has benefited the RFIC community in significant and broad-based ways. And the winner of this year's Tina Quach Service Award is Professor and IEEE Fellow Bertan Bakaloglu from Arizona State University. I am also pleased to say that the Executive Committee has overwhelmingly endorsed Professor Bakaloglu, given his outstanding and long-standing service record to the conference and to the RFIC community as a whole, as listed here in this slide. Congratulations, Professor Bakaloglu. And now it is time for the last segment of our session, which are the plenary talks. Before I introduce the plenary speakers, however, I would like to note for our audience that they can post questions to the 2 plenary speakers using the poll button on the webpage. So please utilize this opportunity to engage with our speakers. And without further ado, I would like to introduce our first plenary speaker, Dr. Thomas Chu. Dr. Chu is a corporate executive VP of the System LSI business in Samsung Electronics Device Solution Division, responsible for centralized development of SoC design and verification platform and various core IP and ICs, including RF analog mixed signal and multimedia. Prior to his current role, he served as Senior VP from 2016 to 2018 and as VP from 2012 to 2015, managing the development of cellular and connectivity RFICs and data converters for several generations of the Exynos modern platform. Prior to joining Samsung Electronics in 2012, he was with several Silicon Valley companies, including Marvell, Intel, and Level 1 Communications, and led the development of numerous CMOS RF analog mixed signal ICs for both wireless and wireline communication applications. Dr. Chu earned his BS degree from the University of California at Los Angeles and his MS and PhD degrees from UC Berkeley, all in electrical engineering. He holds over 40 patents in RF, analog, and mixed signal circuits and systems, and has authored and co-authored over 50 conference and journal papers. Please welcome Dr. Chu.
From the year 2000 to 2020, there were 2 big trends in CMOS RF. These are what I'm calling waves. The first wave was enabled by scaling. Process scaling contributed to the reduction of die size and power reduction. The second wave, fueled by the digital signal processing, enabled the rapid increase of the smartphone usage in 2010. If you look at the smartphone market, it reached its peak and has stood still since 2017. The wireless industry is trying to regain the momentum by having 5G as a new platform. We expect 5G will deliver a higher data rate and lower latency and more reliability. CMOS is a good process for digital, but it's not a good process for RF circuits. The current gain is low and substrate is shared with very noisy digital circuits. RF engineers have to become more creative in preparing the next generation RF solutions. We are facing three big challenges. First one is RF performance gain from scaling has slowed down significantly. Scaling alone does not guarantee a better product. And secondly, the frequency band below 6 GHz is quite busy and crowded. If you want to have a higher data rate, you need to go to higher frequencies. And this is what's happening in 5G. These circuits have to work harder, and that consumes a lot of power. Low cost and low power, those are the two most important things. Digital connectivity is no longer just nice to have convenience. It is basically an instrumental part of our life. We're going to have 40 billion wireless devices by 2025. That's a lot of devices. At the end of the day, the onset of the third wave in CMOS RF really depends on how successfully all these new applications come together in digitally connected ways. It will be a very interesting period to see. Good morning and good afternoon or good evening, wherever you are. My promotional video, I was wearing a mask, and this is me without the mask today. And thanks to the virtual format of the conference. My name is Thomas Cho, and I'm with System LSI in Samsung Electronics. Today, I want to talk about the future of CMOS. But first, let me begin with a picture of present. Well, this is a picture that needs no explanation to the audience today. COVID-19 has affected the whole world, and this is why we are having this conference online. And coronavirus hit South Korea, where I live, around February of this year. We initially thought that it would go away after a short while, but we all know that it was not the case when it came to this virus. The virus is extremely contagious, and the number of COVID-19 cases grew exponentially. And the government and the whole society had to react immediately. I would like to take this opportunity to recognize the dedication and efforts by the medical professionals, by the way. Doctors, nurses, and healthcare professionals, they have been spending days and nights in the hospital, wearing protective suits to take care of the patients. And they are the true heroes of our time. And this is the case not just in Korea, but also worldwide. But their dedication and hard work needed support. And thankfully, wireless technology has been used extensively in these crucial moments. We needed a way to stop the spread in the first place. Well, South Korean government used the 3T strategy: test, trace, and treat. And these are pictures for drive-through testing, contact tracing, and disinfection treatment. And IT supported the implementation of the second T, contact tracing. This is a map of Seoul, the capital city of Korea. Seoul has a population of 9.8 million people. For comparison, New York City has 8.4 million. The marks on the map are a snapshot in time, indicating the locations visited by a COVID-19 infected case. Once the new infection is identified, contact tracing information was used to warn other people who might have been exposed to the virus. Then more tests were conducted to find and stop further spreading. This tracing was possible thanks to the GPS in the smartphone and the electronic record of the credit card payments. The implementation of the 3T has been so far quite effective. And this graph shows the number of COVID-19 confirmed cases as a function of time, starting from the 100th confirmed case. Cases spiked quickly, but thankfully, after about a month from the 100th case, the curve started to taper off. I believe that if smartphones weren't available, the effort to try to contain the virus would have taken much longer, given how densely populated Korean cities are. Also, the fact that almost everyone in Korea has his or her own smartphone helped. And this graph shows the percentage of mobile and smartphone users in different countries. Stats show that in 2017, more than 90% of the Korean population owned a mobile phone, and more than 90% of the mobile phones were smartphones. And most other countries are also hovering around the same numbers. And I would like to assume these numbers would be higher in 2020. So what made this high rate of smartphone usage possible? Well, CMOS RF, my topic for today, and that has been key in the proliferation of wireless devices. As we all know, CMOS is a process technology that led the digital revolution of the last half century. And similarly, CMOS also made the low-cost RFICs possible for massive deployment of wireless devices in the market. But this came about only within the recent 2 decades. The rest of this talk is split into 2 sections. First, I will provide some background on CMOS RF. Then I will highlight 2 trends where respective wireless devices with CMOS RFICs were massively deployed to the market. I will call each trend a wave. Second, based on what has happened until now, I'll discuss what insights we can harvest for the future, a third wave. First, some background on CMOS RF. The incubation period happened around 1980s to 2000. And based on the publications, there were no CMOS products for RF applications yet. But we could find some publications for experimental prototype chips, such as what is shown here. And this is a picture of 1.75 micron CMOS FM receiver covering the FM band from 50 to 100 megahertz. The work was published in 1986. But after this work, there was a quiet period again until universities began to pick up the work a few years later. And why was CMOS not popular then? Well, CMOS is good to make digital circuits, but there are many drawbacks for RF applications, especially if you compare CMOS with more RF-friendly processes like bipolar gas. The channel length was around 1 micron at this time. And let me explain this with several examples. First, the CMOS current gain is typically lower than bipolar as shown in the figure on the left. This is so because the current flows like a thin sheet under the gate oxide in CMOS, while the current flows in a vertical column in bipolar. And also CMOS has higher noise level than bipolar. The figure on the right shows the comparison of the flicker noise, which is critical for oscillator design. And CMOS noise level was again much higher. A second significant drawback for CMOS was the switching noise coupling from digital. The microvolt level sensitive RF circuit had to share the same substrate with the volt level switching digital circuits. The figure here shows an experimental setup to directly measure the switching noise of digital circuits as a function of distance to see how bad it could be. Well, there were some more studies back then, but noise coupling in CMOS still remain on the watch list even today. Now the third drawback. We also know that high Q inductors are key components to make good low noise oscillators as well as highly selective tuned RF amplifiers. But in CMOS, the achievable inductor Q then was a single digit due to the high series metal resistance in the winding and the eddy current loss in the substrate. This in turn resulted in burning large amount of current to achieve the required RF performance level. However, CMOS technology had potential to provide low cost and high integration capability, which outweighed all these drawbacks. And several universities in the US and Europe started to do research on CMOS RF. And pictures here show some of their early works from 1993 to 1997. Initially, they started with individual building blocks like RF amplifiers and VCOs to test out the feasibility. And several attempts were made in order to further explore the new technology. For example, researchers experimented with etching out the substrate under the inductor in an effort to obtain high quality factor for the large value on-chip inductor. And design scale also grew. On the lower right-hand corner, the whole receiver path, including the A to D converter, was designed to demonstrate CMOS's capability for high level of integration. And just a few years later, products began to appear. This picture, published in 1999, shows a CMOS RFIC product. I know the detail well because I also participated in the design of this chip. It had integrated all the signal path blocks as well as the frequency synthesizer. A few advanced features like on-chip power amplifier and on-chip TR switch function were already there too. It was also a direct conversion receiver, and a lot of effort was spent to handle the famous DC offset problem due to self-mixing. This was done by using the feedback-based high-pass filtering as shown. But there were still concerns for integrating everything on a chip, and a few passive components had to be left out. Of course, today, everything has been integrated. Then in the year 2000, more and more companies, including startups, began to introduce Wi-Fi and Bluetooth modem products for PC and laptop applications. They provide the ability to move around within the area while remaining connected to the network without the LAN cable. Well, this is so natural today, but it was such a sensational and new experience back then. And these products and technical capabilities encapsulate the first wave of CMOS RFIC until around 2010. But although growing in volume, early wireless devices needed more improvement in power and die size. There were also lots of exploration efforts trying to find the optimum points in the design. For example, different radio architectures were tried in order to find the one most suitable for CMOS RFIC. Well, was there a winner? I won't say there was a winner, but the direct conversion architecture turned out to be the most popular one due to its simplicity, and that does not have any image problem either. Also, more things were integrated onto the chip in order to keep reducing the cost. At first, it was natural to have a separate RFIC chip in order to stay away from the noisy digital. But the need for cost reduction outweighed this kind of concern, and putting both RF and digital into a single chip as an RFIC became a common practice. And after figuring out how to do this, the industry went further by integrating multiple radios like Wi-Fi, Bluetooth, FM on the same chip. And it turned out that it wasn't too bad. CMOS RF also got some help from Moore's Law. This figure shows the technology nodes that were used for wireless LAN IC papers from 2000 to 2010. And while wireless LAN SoC had both RF and digital, and a newer process was used to reduce the digital area for low cost. And on the RF side, the area shrink was not as dramatic as on the digital side, because a certain level of transistor dimension had to be used for gain and noise reasons. But scaling did help in reducing the power consumption as it pushed the transistor FT above several tens of gigahertz. As Wi-Fi became a default option in laptops, the device shipment surged, as shown on the right. The early shipment number reached 1 billion by 2010, and the number continues to grow even today. Also, as the number of devices grew exponentially, new standards had to come out to provide more network capacity and higher data capability. For example, 802.11a can provide 54 megabit per second in year 2000, but after about 10 years, 802.11n's max data rate has increased to 600 megabit per second. This was done by increasing the bandwidth from 20 megahertz to 40 megahertz and the number of MIMO streams from 1 to 4. And smartphones were the key product for the second wave in CMOS RF. After the first touchscreen smartphones were introduced to the market in around 2007, smartphone shipments increased exponentially. At the same time, the number of cellular phone users also grew fast, and the mobile carriers had to worry about the base station's capacity. They needed a quick solution to this capacity problem, and digital signal processing came in for the rescue. According to the famous Shannon's limit, increasing the channel capacity is straightforward, at least in concept. Based on this formula, capacity depends on three parameters: the number of antennas, the total signal bandwidth, and the SNR of the signal. Increasing each one would result in a capacity increase, and that's what happened during the second wave. Let's take a look at each item. First, MIMO. MIMO stands for multiple input and multiple output. It means using more than one antenna in the system. And according to the formula, having more antennas can increase the capacity proportionally. And this picture shows an example of 4x4 MIMO, where 4 antennas were used to boost the data rate by a factor of 4. Next, the formula says the wider the bandwidth, the more data you can send. So carrier aggregation is a wireless communication technique where multiple carriers are combined into one channel to enhance the overall data capacity. The bandwidth for each carrier can be also increased. And LTE uses this technique extensively, and you can see the data rate increase from 100 megabit per second in 2013 to 3.8 gigabit per second in 2020, almost 40 times increase. The last item, SNR increase. Again, the formula says that increasing the SNR can increase the channel capacity. Well, this means that larger constellation QAM signal can send more bits per second, more bits per symbol with higher spectral efficiency. And this figure shows that 64 QAM can send 6 bits per symbol, while 1024 QAM sends 10 bits per symbol. The data rate that was 150 megabit per second in 2008 got increased to 250 megabit per second in 2018 for the same 20 megahertz 2x2 downlink case. As a result, smartphone use surged globally from 2010 to 2020. This figure shows the installed base of connected devices by segment, and among many different products, we can easily see that the smartphone is by far the largest here. And this is what I call the second wave. Well, we quickly went over what happened to CMOS RF in the recent 20 years. Now, we are in the year 2020. The question is if a third wave would come next. If so, when and how? Well, to find a clue for these questions, first let's take a look at where we are today. The second wave, which was led by the smartphone, indeed was big, but recently it seems to be reaching the saturation point, as shown on this yearly device shipment graph. Since around 2017, the shipment curve has plateaued, hinting that the market might be saturated. Well, knowing that the world population is 7.8 billion, this is somewhat understandable. Anticipating this, the engineering community has been preparing many new applications such as AR, VR, self-driving car, smart factory, smart city, and the list keeps growing. And we can notice that all of these data-driven applications and most of the devices need to have wireless connections to the network. Then the next question, can we simply reuse existing wireless infrastructures like Wi-Fi, Bluetooth, and LTE? Well, I think the answer is not enough. According to a report by Strategy Analytics, the number of installed devices could reach 39 billion by 2025. Today, we have approximately 27 billion installed devices. So that's a very large number. And therefore, we need 5G devices and capacity not only to replace 4G devices for better smartphone services, but also to enable other new applications. But things in life don't always go as planned. From the past, we've seen the rise and fall of many new applications. So we should see what we can learn. I noticed that the applications that remain relevant has several things in common. They were all easy to use, providing convenience, and essential for work and life, and affordable to use. So if you look at the keywords of the first two waves, we can see why. And how about the third wave then? Well, it is still too early to tell what the keywords should be in the box, because the third wave hasn't come yet. But what we can guess is that when it comes, it is most likely that the box would contain a longer list of keywords rather than just one or two words like in the past. In the end, the onset of the next wave really depends on how successfully wireless-enabled new applications could come and rise together in digitally connected ways. COVID-19 will also add to the wins for the third wave list. Even during physical distancing, digital connectivity allowed us to be socially connected so that our daily life could move on. Contact tracing, video conferencing, working from home, online education, telemedicine are some of the examples that show our lifestyle changes through digital connectivity during this time. And reports are showing that data traffic has gone up significantly as a consequence of COVID-19 lockdowns. And some people predict that some of these lifestyle changes may be permanent, but we'll see. How about the technology side? Are we ready for the third wave? Can we continue lowering the cost and power consumption as before? Well, engineers always have technical challenges, but the set of challenges we have today are related to the more fundamental limits, and that's what makes our job more interesting today. For example, newer deep submicron processes give less RF performance gain from scaling than before. Transistors have less self-gain and the headroom for the signal swing is smaller, while the thermal noise level remains the same. Also, the wafer cost is higher, so scaling alone does not guarantee a better product. Also, sub-6 GHz spectrum is quite busy and crowded, pushing new standards to use higher frequency like millimeter wave bands. While it is challenging to design CMOS RFICs that work well in these high frequencies. Then what are the options? Well, we should expand our view more. There are different layers in the design hierarchy, and the trend shows that our focus should move more to the top because RF performance gain is coming less from the bottom. So it is increasingly more important to find system-level solutions through hierarchical co-design and optimization. By the way, I wouldn't say that the story at the bottom is over yet, because process engineers also have been very creative so far. And in the following slides, let me show several examples of RF designs that illustrate this point. First example is about reconfigurable design. The diagram on the left is a multifunctional RF SoC that supports both narrowband IoT and GNSS. And the straightforward way to realize this multifunctional radio is to integrate our IoT and GNSS RF IPs side by side. However, we noticed that the NB-IoT and GNSS can operate in different time. So we made the envelope-based hardware reconfigurable to save the area. This work was published this year at ICC. Second example is about the circuit level streamlining. As system aside, we've designed several generations of RFICs in 14 nanometer for cellular applications. And 3 of them are shown here. And we can see that significant power reduction was possible just by carefully redoing the design and layout. In addition, we are able to reduce the die size by 30% between N+1 and N+2 generations. And this suggests that there are still lots of room for improvement, even by using the same process node. We just need to look more closely and more carefully. Also, we know that more chips you put on the table, more things you can play with. Here's a set of chips which you can typically find in the smartphone. And today, most data traffic is due to pictures and videos from multimedia devices. And the data traffic conditions could vary a lot depending on the operating scenarios. In this case, PMIC can vary the supply voltage level to RFIC accordingly, and more power saving can be achieved compared to the fixed supply voltage case. By the way, many of these techniques are not new. To achieve more improvement, we just need to come out of our comfort zone and reach out consistently to other engineers across multiple disciplines to come up with the new ideas. We should also look for collective innovations at the design boundary. I listed keywords for the trend at each boundary point here. And notice that each boundary point is not independent from each other. So engineers must have good understanding of the interdependencies in order to make smart design trade-offs or to invent a completely new solution going beyond the boundaries. For example, millimeter wave frequency operation would need many antennas to do beamforming for the required link budget. But having too many antennas can be expensive because each antenna needs a power amplifier. And having many power amplifiers would mean a cost increase due to die size increase. Then it may not fit in the given space within the phone. Then you may have to look for other power efficient non-CMOS power amplifiers to reduce the array size. And the story can continue on and on. So engineering exercises are getting more interesting, and today's engineering community should react to this type of new challenges. Finally, the summary. The third wave wins or new applications are building up. And from the past, we learned that applications must be convenient, essential, and affordable to be successfully deployed and to endure in the market. And COVID-19 came as a surprise, and it is accelerating deeper digital connectivity adoption in our life. More CMOS RF cost and power reduction will now come from the top, requiring better system-level co-design and optimization. We also need to look for collective innovations at the design boundary points. Okay, so before I really end, I'd like to thank Sang-Hyun Baek and Andrea Soto and colleagues at System LSI for their help in preparing this talk. Thank you for your attention, and I'd like to answer your questions if you have any. Please ask me now.
Okay, now I'm opening up to any questions you may have. Okay, so what is the question is, what is the highest frequency that you will see in the mobile device? That's a very good question. It's not a difficult question. For 10 years, it's too far out, but I can say that for 5 years. Right now, for the definitely for 5G FR2 applications, we are looking at frequency ranges from 28 or 24 to about 39 to 40 gigahertz. So we'll be some in that range. Some people talk about terahertz applications, which is above 100 gigahertz, but I think it's further out. So I'll say for the next 5 years, the highest frequency will be about 40 to 50 gigahertz, under 50 gigahertz in that range. Of course, what are the associated challenges? Definitely, it's a high frequency is, there are, for CMOS applications, the modeling is definitely critical. Device modeling is critical, and also system design is critical. As I mentioned in my talk toward the last part, I talk about how the system design, antenna design, and circuit design, they're all related to each other. So we engineers must understand the whole design hierarchies and need to optimize to come up with the best solutions. And oftentimes, digital and RF side, they are kind of separate, but this time we all need to come together and then need to work together to come up with the best solutions. Well, again, as I mentioned, the scaling definitely helped in the past, but it kind of slowed down for RF applications. Therefore, we need to come up with more system solutions. I believe this conference is about, the focus is also moving toward the system design as well. So I think the conference is also addressing the right direction. Okay, so the question is whether 2.5D or 3D design will be used for pure RF applications. Definitely for millimeter wave applications, the distance between antenna and the chip needs to be very small. So therefore, people are using different module technologies to put antenna right on top of the chip. And we've seen this example before in 60 gigahertz applications. And also for millimeter wave applications, for the 5G millimeter wave applications as well, you'll see this kind of design. So in that sense, yeah, 3D is happening, yeah. Okay, I believe ITRS, I think I've seen this long time ago, but yeah, it was talking about, they were predicting the slowdown of the scaling and how other technologies, for example, packaging, sensors, actuators, and different kind of technologies would help to further continue the improve the solution, improve the chip designs. And yeah, it was, I read this many years ago, and then it was very helpful in predicting the future, and looks like things are happening in the direction that ITRS predicted. Okay, the question is how's AI impact the future RF design? Well, AI is almost everywhere if you look at chip design, especially on the video imaging and other side. But on the RF side, I haven't seen much applications yet. However, I do see more AI being used in modem. People are trying to use that to further improve the modem performance. So RFIC, we haven't tried it yet, but I think it could be a matter of time. I'm pretty sure some people will come up with a neat idea on how to apply that AI to RFIC. We just need to wait and see and how that happens. Yeah, but I don't have a clear answer yet. Whether computing power, the question is whether computing power will limit the AI for RF application. Again, I haven't seen the example yet, so it may be, but it may be not. It really depends on where it will be used and how it will be applied to the RF applications. So I don't have a clear answer for that, but we need to wait and see. Okay, the question is whether the fancy processes like gallium nitride or SiGe processes will be used for future. Definitely, they will find applications. Whether they will be used for mobile applications, that's a different question. Usually, gallium nitride is for base station applications for very high power. For mobile application, I don't think it will be used. But for there is also other technology like gas, silicon, germanium, and also SOI technologies. I think those are good candidates to further enhance the RF front-end performance. So transceiver will still remain in CMOS, but the RF, especially at very high frequency, those non-CMOS technologies could come in and help for power efficiency. Well, that was that's a very interesting question. But that's a very good question. We tried to move the analog. Oh yes, the question is whether we could directly sample the signal at the antenna. That is a very good question, and people try to move the analog to digital boundary much closer to antenna, and it actually did, and we tried to minimize the analog portion of the whole modem, but hasn't come to the front end yet. It really depends on how you can make the data converter, whether you can really make the data converter very low power, low noise, and with the very clean clock source. So it boils down to how you can make it. So at very high frequency, it will be still difficult, but at low frequency, there were cases like a FM radio. I think our company had a paper at ISCC where we directly sampled the antenna signal through the A to D converter and then recover the FM signal. So depending on the frequencies, it could happen. Yeah. Well, that was the last question, and thank you for having me for this conference. And please enjoy the rest of the conference. There are lots of interesting stuff here. Thank you.
Thank you, Dr. Cho, for this exciting and informative talk, and thank you for answering the audience questions. I wanted to just note one thing on Dr. Cho's slide 13 was showing many breakthroughs that happened in 1997. And coincidentally, this is actually the same year that we founded RFIC. So we are almost up to our 25th anniversary here. And Dr. Cho has given us a look at the past of how this happened and actually how RFIC was incepted as well. The symposium was incepted as well. With that, I would like to, before we move to the next plenary talk, I would like to thank and award this plaque to Dr. Cho on behalf of the RFIC Technical Committee. Thank you, Dr. Cho, and appreciate the effort. And now I'd like to introduce our second plenary speaker, Professor Hajimiri. Again, please make sure that you post your question to Professor Hajimiri using the poll button. Professor Hajimiri is the Brin Professor of Electrical and Medical Engineering at California Institute of Technology, where he has served as a faculty member since 1998. He has had several appointments in the industry and has co-founded several startup companies in the field of RFIC, such as Axiom Micro Devices, whose fully integrated CMOS PA has shipped around 400 million units and was acquired by Skyworks subsequently. Professor Hajimiri has authored and co-authored more than 200 journal and conference technical articles. He has been granted more than 100 US patents and has many more pending applications. He is a fellow of National Academy of Inventors. Professor Hajimiri was selected to the TR35 Top Innovators list. He is also a fellow of IEEE and has served as distinguished lecturer of the Solid State and Microwave Societies. He won the Feynman Prize for Excellence in Teaching, Caltech's most prestigious teaching honor. He was a co-recipient of the Journal of Solid State Circuit Best Paper Award, the Solid State Circuits Conference Jack Kilby Outstanding Paper Award, a co-recipient of RFIC Best Paper Award, and a two-time co-recipient of the CICC Best Paper Award. Without further ado, I'd like to introduce and welcome Dr. Hajimiri.
Connectivity is at the heart of humanity. As more and more people are connected through technologies that we are developing, we have to always take steps forward and we have to go beyond where we've gone. At Caltech, my research group focuses on applications of integrated circuits from communications to sensing and wireless power transfer. CMOS stands for Complementary Metal Oxide Semiconductor Technology. It's a technology that allows you to integrate practically an infinite number of transistors. The largest chips that we can make today have more chip transistors on them than there are people on this planet. And my joke goes, unlike the people on the planet, every single one of those transistors work. Using CMOS for radio frequency and high frequency and microwave and millimeter wave has gone from being science fiction to something that's the bread and butter of every piece of technology that we have today. This is a CMOS chip that essentially it's a radar on a chip. It's used for autonomous vehicles. The camera that's taking this video right now, it has a CMOS image sensor and a lot of CMOS processing capabilities. The other thing that I'm very excited about is using this technology, particularly for people who are visually impaired or if you're hearing impaired. You can make a special shirt and it provides input to them either through audio or haptic or a combination of those things that gives them a sense of what's going on around them. The CMOS chip is used in conjunction with a flexible material where you can form an array. This can be actually part of a wireless power transfer. It enables you to remove direct wired connectivity and turn everything into a wireless system. What I'm mostly excited about is basically the convergence of all of these wireless applications. Communication, sensing, and power, making it more ubiquitous across the globe. It provides an opportunity to have everyone on this planet connect and in a way giving the voice to the voiceless. One of the things that I remember my dad telling me is that the future never loses to the past. The number of opportunities that are out there and we haven't explored exceeds significantly what we have done so far. Good morning, good afternoon, good evening, and good night, wherever you are. Thank you for joining me for this live presentation of the RFIC plenary session. So the title of the talk today is The Flexible Future of RF. And we are going to tell you what we mean by this flexible title. And what you see is that a lot of the focus was basically, the basic story was the same. It's a way of turning sand into money through silicon. But, and a lot of the focus, of course, was on using integrated circuits, but a lot of the focus was on the component levels and block levels, LNAs, power amplifiers, mixers, and so on and so forth. And we started just thinking about these architectural things and using phased arrays and things of that sort, for example, a 24 gigahertz system and things of that sort. But I thought that if you're going to look at the future, we need to start looking at the past and see how that past ties into the future. So if we go back in history a little bit farther back, pre-RFIC dominance, the way the microwave design was done and the RF design was done, it was essentially a classical microwave design. And the idea here was that we have, as you can see in the slide, a large number of discrete components attached to each other. A lot of these things are actually connected through strip lines, and this originated in microwaves. And then we continued from that, and then we went on and decided, and a lot of the system spec were coming top down. In essence, a lot of the people with background in discrete circuits and all those things gave that system definition, and it flew down. Basically, it was flown down to the lower levels of RF designers. So the flow down was going in that direction. Now, one of the things that happened, and there was an allusion to this in the earlier presentation as well, is that in the late 90s and early 2000s, RFIC was still being considered an academic exercise. There were these ISSCC panels literally titled, does CMOS make sense for RF? And a lot of visionaries said no. And a lot of the discussion, everything had to be proven. And the way that it was looked at is that, okay, I have this compound semiconductor or gas component, and can you give me a component that's comparable to that, but it's a little bit cheaper? Can you make the LNA noise figure comparable, or the PA output power, et cetera, et cetera? And most of the RFIC architectures and topology, the architectures that were used, essentially were borrowed from discrete RF CMOS design, RF and microwave design. And basically, and this is a very different trade-off, because in that point, you have expensive transistors, cheap passives, and large mismatches among the devices. And if you brought up the discussion and said, well, perhaps we need to change the architectures to address this the best way, the answer became very quickly just like, okay, this is an academic exercise, really, and academic wishful thinking. But RFIC was different. RFIC fundamentally has many differences. For example, there are challenges that there's a lot of crosstalk. There is the breakdown voltage challenges that are basically going down instead of going up. But at the same time, things stay lumped up to much higher frequencies because of the smaller sizes. And you have basically very reasonably much better matching for the circuitry for the components on chip. And then going off chip is the hard part. So you want to stay on chip as long as you can. So it's a very different mindset. So if you do something that may cost you a little bit of extra, but it allows you not to go off chip, it's a major advantage. So these things led to some of these early developments of block level and component levels. And then there was a transition period where there was a general realization that as you go from these topologies, and architecture needed to change to adapt to this new change in the trade space. Now, and the other thing that became clear is that the advantages of moving to higher frequencies, because as you move to higher frequencies, what happened is that the integration became more, RF integration, electromagnetic integration became part of the system. And then it allowed you to make truly combined active circuitry in this setting. So you can have actually a lot of active circuitry intertwined with your passives. doing functions that are very interesting. And these are examples from the past, kind of like that doing 1 gigabit per second at 24 gigahertz, in 2005, and so on and so forth, and 77 gigahertz and 300 gigahertz systems that were demonstrated. Now, one of the things that happened is that there was this long-term trend that went on, and it's really the change that really comes from the realization that the transistors are practically free, incrementally free. And what happens is that we have to change, we realize that we have to change our mindset, going from a small number of large components to a large number of small components, from a centralized to decentralized. And that's what's going to continue to happen at multiple levels of abstractions, anyway from component level to architectural level, topology architecture level, and all the way up to algorithmic level and protocol level and the system level. And that's basically what matters the most, and it will affect the way we design things the most going forward. And so this is, one of these interesting things that comes out of this picture from the famous book, The Wizard of Oz, which is the interesting thing. The most powerful wizard was the one that actually didn't have any power, and was basically a man who used ordinary forces of nature to get what's going on, which is essentially what the engineers do. Now, so let me just give you several examples of this mindset and how they apply. So, for example, now think about flexible phased array. Think about a situation where you have a very ultralight portable system. This is something that you can roll, flex, and it allows you to make it modular. Basically, you can stamp it over and over, and then basically you can have something that's collapsible and extremely lightweight that does some RF functions. Now, it performs a series of RF functions. And when you have something like this, you can think about a lot of application, from active fabric, for terrestrial communication, for space deployable structures, and so on and so forth. And these are the kind of structures we're talking about. So let me just give you an example. So if you look at this picture, for example, so these are the kind of consistencies and properties that we're talking about. And it's very important to realize that this opens up a new set of applications. Anything from wearables, as you can see in this slide, the next slide that we can see. So you have a bunch of wearables. You can have basically devices that you wear on your body. You can have a shirt. You can have a kind of like a wristwatch, or any kind of device that can be used for medical monitoring, can be used for general sensing or actuations or what have you. And this is one example of the things you can have. Another example is, of course, a space-based communication. You can also have what I like to call internet above the clouds. And here, the idea here is that if you can deploy these devices in a lightweight fashion, if you make these lightweight self-powered devices, what it allows you to do is to deploy them at low cost. And you can have a large number of them providing internet access from a low Earth orbit, LEO orbit, and allows you to have a very decentralized way of covering the globe and democratization of access. Another application a little bit farther out in terms of being ambitious is the space solar power. The idea of space solar power has been around for a long time. It started in science fiction, and so far it has remained kind of more on the science fiction realm, but it also enables a large number of interesting applications in principle, and the developed technology can also be used for a lot of other things. So the idea here is that you have very lightweight sail-like structures in space that collect the RF energy, the solar energy converted to the electricity, and that electricity is transmitted as RF signal, forming a beam and transmitted to the desired location. Now, at Caltech, we've been looking at this technology and this concept, and our concept is essentially based on a highly modular design, where you have different modules, each consisting of a large number of smaller units that work together. And there are, as I will show you later on, we use RFICs to enable something like that. They have to be very lightweight, and they will be flying in formation. And this can be used for dense array, for example, in wireless power transfers applications that we'll talk about in a second, as well as sparse arrays, which are applicable for communications and remote sensing. So these systems are built in a hierarchical fashion. So if you think about it, the smallest building block of this system is what we call a tile, something you can hold in your hand, and I'll show you examples of. And then you can put them into larger strips and panels that you can connect together. And then these come together to form modules that are much larger and can be anywhere between 10 meters to 60 meters on the side. And these modules eventually can formation fly and form an entire system that can take the power and convert it to RF and transmit it to ground, or use for other applications. Now, of course, such structures require interesting packaging, and they have to be done in an interesting way. So, for example, here's one of these packaging schemes where they actually roll them. Since they are collapsible and deployable, you can roll them, you can wrap them, and then you can unwrap them. And these are some practical examples of how this wrapping and unwrapping actually happens using these structures. Now, once you have something like this, the advantage is that the power is generated locally, and it's basically converted to RF locally. So you eliminate all of the DC distribution lines in the system, and all you need to distribute is the timing information and control signals. And all of the power signal is basically generated locally and transmitted locally, one way or another. Now, the building block, let's talk a little bit about this building block, the so-called tile. The tile in the system or all of the functions are integrated into an RFIC, a single RFIC. So basically, this is responsible, and I'll tell you a little bit more about this RFIC, to convert the DC power to RF, do all the synchronization, beamforming, focusing, all of the wireless power transfer and communication aspects associated with that. Now, the RFIC by itself is very conducive to this kind of application, because one of the important things, especially for space application, but also for all sorts of other applications, is the mass. And RFICs, as everyone knows, they're quite low mass. So this is, for example, you put one of these chips on a scale, and what you see here is that basically it's like 8.5 milligrams. And these chips are pretty sophisticated. So each one of them basically can provide power to 16 different outputs. There are 17 PLLs on each one of these chips. And here's a little bit of a hierarchical quick tour of this IC, if you will. And what you have here, this is a high level. So each side of the IC, each one of the 4 sides, is what we call a power quadrant. And a power quadrant consists of 4 outputs that can be independently controlled, and they're driven they are basically the input to this. If the timing reference comes at a low frequency, let's say 50 megahertz or 100 megahertz, there's an on-chip PLL that converts it to 2.5 gigahertz, and then there are all additional on-chip PLLs on each one of the quadrants that are shown here that converts that to that frequency of operation. In this case, it's near 10 gigahertz. And what happens here is that essentially you can control the phase of each one of them in different fashions. You can do it quickly if you want to do communications, or you can do it slowly if you want to kind of do other kind of stationary control. And interestingly, in this case, for example, all 4 power amp cores on each quadrant are stacked DC-wise, so they share the DC to be able to operate off of a larger DC voltage, but at the same time, they are providing independent power. And if you look at each one of these power cores, that's one of these we are just diving deeper and deeper into this thing. It's a pretty sophisticated system in itself. It's a chain of amplifiers with independent power control, local sensing and detection and control for power, voltage, and temperature independence operation, and a fair number of other capabilities associated with that. So this is part of the system. The other part is, of course, the radiative part. And then it needs to be collapsible. So in this case, we have basically these designs that I'm showing in this example, a design based on patch antennas. And this design based on the patch antennas, in this case, are collapsible. So you have a second layer that will collapse on the first one. It slides on, and when it's deployed, it opens up. And what this allows you to do is to basically have a very thin sheet that you can actually roll and store, and then just deploy as you go. And so here's an example of that. And what you can see is that they're quite thin. You can see that it's almost translucent. And this is an example of one of these tiles that you can make as you go. And there's a first generation and second generation of these tiles that are shown here. We made a second generation of that. And you can see this tile that now, in this case, so it's actually also augmented with the photovoltaics that collect the power from the sun, the PV, and then it's concentrated, and the RF. So this is a combination of all those things. The RF part of it is about 7 grams in total. And these are pretty flexible. And what you see here, for example, I'm holding one of these in my hand, and you can see that they are quite flexible. You can actually bend them. And then there's the RFIC chip on the back side of it. And as you can see in the slides as well, these can be bent, twisted, and turned, and they can collapse and release themselves. And now, at the same time, they're functional, which is quite important, in the sense that if you look at it, for example, they can perform both what we call the near field or Fresnel region, radiative near field, and far field focusing functions such as focusing and RF lensing. So what you see here in this example is an example of RF lensing when you create a local focal point, similar to what a lens does. And basically, you can see it in the distribution of the field, the hologram that's shown on the bottom right side of the slide, how something like that actually works. Now, to show you an actual physical demonstration of this thing, here's a video of how that actually runs in practice. So here what we have a solar simulator that illuminates the top part, which where the photovoltaics are. They generate the power, and the bottom part, which is the array, is transmitting the power wirelessly, and you can see it being received from the bottom side. And you know what I'm doing here is that I'm putting my hand in there to show that it's actually the power that's being wirelessly received. In a second, you will see that, and then also. Next, what you will see is that it's a view from the bottom, so you can see the elements. Now, all of those 16 elements are driven by a single RFIC chip that we just showed you as an example of what some of the things that you can actually do using something like this. So now this is that unit building block, and then you can use it to make larger systems. And so here, basically, what we see next is an example of how this basically would be scaling up. So this is an example, and this is a talk at IMS this year. I encourage you to go and see, watch the video for more details of that. So this is a 256 radiators. This is 256 elements that uses 16 RFICs, and you can see that it's basically just scaling up in a very scalable, modular fashion. And what it does, it's interesting because then once you make an array of this kind and of this size, then you need to have interesting new algorithms, which is also an interesting subject that is kind of quite a rich subject to look into in terms of what can be done. And essentially, what we show next is basically some of the radiative measurements of this thing. So you can see that this allows you to form a focal point straight ahead. And you see 5 different plots on the right-hand side, to the top, to the bottom, to the right, and to the left. And so you can see that actually you can form different spots in different locations using this. And now this is also the more important and interesting part of this thing is that, you know, these things can deform. So you have to make them in such a way that they can deal with that. So for example, on the left-hand side, you can see a spot that's formed, and then the array is deformed. So and then as you can see on the top right, the focusing has diminished for a good part. But now when you do the refocusing, the system is able to correct for that and move forward according to this. Now, to give you a sense of what we are talking about in terms of the mass and all those things. So the current system, basically, we are looking at about 670 grams per meter squared. And then we are expecting within a year to have something around 450 grams per meter squared, areal mass density. This is less than a kilogram per meter square of the entire system. Now, but what we are also working towards designs that are about an order of magnitude, even smaller, and we are targeting towards these asymptotes, really what we call them, which is but the best we think we can be achieved. And to give you a sense, the paper grammage of your regular paper is about 80 grams per meter square. So if you're looking at this like next generation stuff, these are basically lighter than a sheet of paper in terms of the mass that they would carry. And they would present interesting opportunities and challenges when you deal with them. So one of the questions for something like this is that how do you deal with this like flexible surface, because it's very, very floppy, very, very soft. And to do that, actually, we developed a fair number of interesting techniques, a family of techniques which can be applied to it. So for example, this is a one-dimensional array, a different kind of array that can flex and bend. And what we do here is that we have receivers and transmitters incorporated into each one of the elements, that by talking to each other, they can form a local measurement of the system. And from that, they can actually estimate the shape of the system directly. And by estimating it, so for example, in this video, what you can see is that we have this apparatus that takes this and bends it up and down. So it basically flexes the board. And in real time, the system can identify that it has actually changed shape. And as you can see here, and so once it identifies, as you can see from these plots that we are going to show next, and then what you see here next is that as this system detects these changes, it can correct for it. So this plot shows what the power is, received power for a receiver at a fixed location at a distance, with and without the shape correction. And what you see here is that without shape correction, as the system, as it flexes up and down, the correction, without the correction, you lose a lot of the power. But when the correction is actually applied, you can see that the curve is a lot flatter. And that's basically what you see in this from this demonstration. These things also apply, these techniques can be also applied to other devices that intentionally change shape. So for example, there are these origami-inspired systems that we've designed. So these are basically arrays that can change shape to create different kinds of aperture and modify their apertures in real time in response to the system. So this page, for example, shows them in 3 different conformations, and you can see that you can have a flat one, and then you can have a cylindrical or spherical design. And for each one of them, again, there's an RFIC that deals with them, detects the signal, and transmits the signal accordingly. So with something like this, one of the interesting things that you can do is that you can actually enhance your aperture at different angles, and you can have a broad range of angles depending on what setting you want to be in. You can change the behavior of the system entirely and create different kinds of systems. Now, let's take it to another next kind of like an example, which is basically from a more commercial world of, and this applies to applications of wireless power transfer at the distance in particular. So this is some of the work that has been done at the company Guru Wireless. And what this does, basically, this shows the progression of how going to higher frequencies reduces the size of the system, allows you to have more precise focusing, and allows you to have longer range. So this is a comparison of a 2x4 element component, if you will, at 2.4 gigahertz, 5 gigahertz, 10 gigahertz, and 24 gigahertz. And these are all the designs that we've done. And basically, what you can see from this is that by going to higher frequencies, you can actually go farther and reduce the size of the system. Now, you can, of course, applying the same principle of scalable and modular design, you can make very large-scale systems for power transmission. They're using these individual elements, and you can either have them in a static setting where basically you mount them somewhere. You can have them inside the home, on the wall, or on the ceiling, or you could also have something that itself moves around and finds other targets and basically finds devices that need power, be it your phone sitting out there, being it some sort of an IoT device somewhere, and identifies them, finds them, and provides them with power as it goes. And of course, it's paired with the appropriate, what we call the recovery units. So we have the generation units, the GU, and the recovery units that are the RU that work together. And to give you a sense of what kind of things can be done with these things, this video just kind of like showcases a few of these examples of what can be done. So what you see here, so this is an example of a stationary unit, a GU, a generation unit, that's transmitting power at a distance. And what you see here is that you can see these propellers that are at a pretty far distance with respect to them, that are being powered, and they are operating with the power that they wirelessly receive. So this is another example of a receiver. And you can see the system can very dynamically and quickly track the recovery units that's trying to power and send the power, transmit the power there. As you move these units, basically they can very quickly find it and transmit power there. And this is an example of basically sending power to one or another device, and then basically trying to power multiple ones at the same time. So it can basically not only transmit power to a known location, it can transmit to multiple locations. So in this case, there are 4 different locations. So this is a car that doesn't have any batteries, and it's a little toy car. And basically, the system is tracking it and dynamically powering it. So it's basically moving from the power that it's receiving from the wireless power transmission system. And this is another example of a device that actually it's a source of power. So it's like a mini robot that goes around and identifies devices. In this case, they're exemplified by these light bulbs on the wall that are powered through this device as it moves around and powers them. So that was basically the example of this thing. So now let me just wrap up quickly and kind of like try to draw some conclusions. I think that the future of RF and RFIC by extension is very flexible. There are many opportunities. And the interesting thing is that now, because of all these different things that you can create, a lot of the innovations, really fundamental innovations, I'm not talking about incremental changes, small modification to existing systems, will come from the capabilities of RFICs themselves, meaning that identifying that certain capabilities exist allows you to identify new things that you can do with it, and you can be quite creative. And I think there's an incredible amount of new opportunities because of the accessibilities of these technologies. So I am giving you a few examples of those things. I gave you a couple I showed you some of those examples. There's a longer list here of all the things that can be done. Anything from these deployable structures to these decentralized relays and repeaters to lightweight communication hubs to a whole slew of photonics and electronics RFIC systems that can be applied in different places, and RFIC plays a major role in them, as well as medical and implantable devices that also play an important role. Now, I think this is very important, especially talking, and I'm now talking to the younger generation and the young at heart, those of us who are really forward-looking and would like to kind of continue to induce change. This future is flexible, and you have to be careful. If you want to understand the future, you have to also learn from the past to some extent. And here are some cautionary tales from the past. There have been many times that people have said things that, okay, well, you know, there's nothing left in the theoretical physics, or there are no applications for electromagnetic waves, or, you know, nobody needs a computer at their home, or things along the lines of everything that could be invented has already been invented. And this is just a manifestation of not being forward-looking and not having much imagination. But what matters really here is that you need to really create the future. And I think it's incredible that how many opportunities are out there. And this future can be made. And I think you are the future, those of you who are listening to this. And I think it's very important for you to realize that future is built by you, and you can make it a beautiful one. And I think I'd like to end this talk with something that I always heard from my father, and I think I would share it with you, which is that future never loses to the past. And with that, I'd like to conclude the presentation part of it, and I'm open to questions from you. Thank you very much. Okay. Okay, I see some questions here. So one of the questions is that, do you foresee any safety issues with the amount of power density focused out of the array when it's used for power transmission? So this is a great question, and it's a relevant question. So think about it this way. There are certain levels of power that, of course, beyond a certain point, you don't want to be transmitting, mostly because you generate too much heat. Now, these systems have a lot of built-in safety mechanisms into them, first of all, in the sense that they can detect that if somebody is moving them, and I don't know if you noticed in that video that we were showing that they were off for a few seconds, then they turned on. So they can detect if somebody is getting in the way and adjust the power accordingly. Also, what we envision is that as time goes on, similar thing that happened to the cellular phones. When you went from the central broadcast, it's not very safe to stay very close to a TV station or an FM station either. But what happened is that you have more and more transmission units, so you can actually have a smaller and smaller power, and you can reuse the spectrum more effectively that way. So the same thing will eventually happen with these systems. But right now, the power levels are all within the limits that are specified by FCC, and there are also these additional safety mechanisms that are built into the system that allows it to detect if somebody is in the way, if an animate object is inside, getting close to the focusing point, and react to that. So, okay, so let me ask there's another question here. What can you say about the overall efficiency of the system? And the answer to that question is yes. There was a curve. I don't know if you saw it or not. So the efficiency is broken down into different parts, right? There is the efficiency of the RF signal generation. And we know what the PA efficiencies typically are. I mean, you're basically looking at different ranges of efficiencies for power amplifiers. And but keep in mind that these don't have to be modulating, so they don't have to be linear amplifiers. They can actually be highly switching amplifiers, so the efficiency can be reasonably high. Now, there's what we call the transfer efficiency, or some people call it air efficiency, which is basically the efficiency from the transmitter and receiver. And that's a function of the distances and the sizes of the recovery units and the generation units. And those things are basically things that you have in your control. Yes, of course, if you take them and put them very far, the efficiency will start drop. And I don't know if you noticed or not, but in those curves, there was a curve of exactly that efficiency. And then there's the efficiency of recovery or rectification and signal conditioning. That can be quite high, actually. So that's not very low. So it's a product of these three. But also the other thing to keep in mind is that this is the capability that doesn't exist. So, and the analogy I like to use often for this is that it's the difference between Ethernet and Wi-Fi. Ethernet is a lot more efficient than Wi-Fi, but a lot more people use Wi-Fi than Ethernet because it gives you a capability that the Ethernet doesn't. In fact, I think probably I'm one of the very few people who actually calculated the efficiency of Wi-Fi, and it's basically a decimal point with a lot of zeros before you get to the 1. But you still use it because it's a very powerful thing. But the efficiency is not out of the reasonable range, but it's just basically something to keep in mind. So let me look at it. Okay, so let me see. How about the loss from, let me just make sure I can read the question first, and I will repeat it to you. So how about the loss from RFIC to antenna? It looks like the distance from the farthest antenna to RFIC is tens of centimeters. Will it be a big loss of RF power? So actually, well, not necessarily. The answer is that this is basically from the antenna to RFIC, the distance is about basically several centimeters. And this depends on how you design your transmission line. So you don't lose that much power. It depends on a lot of parameters, such as the quality of your copper and conductors and things of that sort. But overall, that's not a major source of loss. I mean, of course, like any other transmission of power and any other, you have some loss in the system, but basically you have this overall efficiency that's quite good for that part. Okay. Okay, so another question is that a significant problem in space is getting heat out of the system, and generally radiators are a big chunk of the system mass. Do you anticipate needing radiators in these flexible arrays to get the heat out? So that's an excellent question. We've actually spent a lot of time looking at the thermal behavior of this thing, and I didn't show any of that, but it's interesting because, first of all, the heat dissipation in space is not by convection. So the kind of heat sinking that you have is very different. That the heat sinks that you have, if you have things with fins, they are pretty useless because they are essentially not going to do anything. It's radiative heat exchange, and we've done extensive modeling of that. So keep in mind that one side of the space is very cold. It's the side that's not facing the sun because you're facing the background. And well, theoretically, it's several kelvins, but actually, because you see the heat of the background of the galaxy and all those things, you're looking at about 20, 25 Kelvin. So you're doing heat exchange with something that's 20, 25 Kelvin. You have to design it in a certain way that it's very conducive to that. And we actually make it out of layers, and we cover it with layers that are have high emissivity at IR and release it. And that basically allows you to do the proper heat exchange in the system. So that's a good question, and this is something that we've looked at, and it's completely manageable. And I think that was the last question, and thank you very much for your attention.
Well, thank you. Well, thank you very much, Professor Hajimiri, for inspiring us with this talk. And on behalf of the RFIC Technical Committee, I would like to present you with this award and plaque. And now we've come to the end of our session. On behalf of our steering executive and technical committee, I would like to thank you all for tuning in and hope that you had the time to enjoy this session and that you will spend more time to enjoy the remaining sessions in our virtual event. And also don't forget to visit our virtual exhibition, because there's quite a few of events that are happening as well there. Thank you all, and we look forward to seeing you in the RFIC 2021 in person next year. Bye-bye.